Okay, welcome back again to CSE 373. It sounds like my first set of videos that I produced had some poor sound quality, and so I'm here re-recording all of them a little bit later the same day. So today we are talking about topological sort, abbreviated topo sort, and reductions. Now, the first 20 or so minutes of today are going to actually be reviewing Dijkstras and talking about some extra things about how to implement Dijkstras and how to analyze its runtime. But then we're going to talk about this topological sort and reductions thing afterward. So in terms of our learning objectives for today, the first one is to be able to describe the runtime for Dijkstra's algorithm and explain where it comes from. Then we want you to be able to define a topological sort and determine whether a given problem can be solved with the topo sort. Then we want you to be able to write code to produce a topological sort and identify valid and invalid topological sorts for a given graph. And then finally, to be able to explain the makeup of a reduction, identify whether algorithms are considered reductions, and to solve problems using these reductions. Again, most of these terms probably don't make sense quite yet. That's totally okay because this is a preview of everything we're going to see in today's videos. So to start off for today, we're going to start with reviewing Dijkstras and then talking about how to implement it and analyze its runtime. So from what we've seen so far, we've talked about a bunch of graph problems. And in some sense, a problem is a very abstract notion of a question you might ask, and you might devise an algorithm to come up with a way of solving a particular problem. So on Wednesday, we introduced the ST connectivity problem, which is given a graph, a starting vertex S and a target vertex T, does there exist a path from S to T? And our solution was an algorithm that used BFS or DFS in a modified sense, so that whenever you encountered a vertex, you checked if it was the target, and if it was, you return true. If you made it through the whole graph, otherwise you return false. We talked about another problem, which is the unweighted shortest path problem, which is given a source vertex S and a target vertex T. What is the shortest path from S to T, where we define shortest in terms of the number of edges. So the path that had the fewest edges is the shortest path. And in that problem, the solution was using BFS in another modified sense, such that we generated this thing called that shortest path tree, keeping track of for each node where we came from, what was the distance to, as we went. And then on Friday, we introduced that weighted shortest path problem, which is the same thing as the unweighted shortest path problem, but we make a key change where we assume each edge has a weight, its label is some number, and the shortest path is defined in terms of the path that has the fewest sum amongst all of the edge weights. And for this problem, we had to introduce an entirely different algorithm called Dijkstra's algorithm to generate the shortest path. Now, to quickly review what Dijkstra's algorithm was, we started with having a known set, a set of nodes that we know the shortest distance to. And then we had this perimeter outside the known set, which are all the nodes that we have looked at because they're adjacent to the known set, but we haven't decided if we know the shortest path quite yet. And this perimeter is what we use to grab the next node. So just like with BFS, we grab a node from the perimeter, but differently, we grab the node that's closest. So kind of distinctly with Dijkstra's, we keep track of this dist2 map, which keeps track of the distance from the start vertex to this current node based off this path length. Now, we always grab this closest unknown vertex, and then we add it to our known set. Then, for each node that's adjacent to that node, we kind of look through and see, well, does the path coming through me, the node that just got added to the known set, is that a shorter path than my current proposal of what I think the shortest path is? If it is, I update my data structures. Now, this algorithm works because we maintain this invariant, such that once we add a vertex as being known to our known set, we are saying we know its shortest path, which conversely means that while a vertex is outside of our known set, there might be a shorter path that we find later. So we can't make any assumptions about that perimeter or anything outside the perimeter of knowing what the shortest path is. And so the kind of key thing that enables this is the fact that we go through the vertices in the perimeter based off the closest one. We always grab this closest vertex, and that kind of guarantees for us that we're never going to kind of find a shorter path later. And to understand that, we talked about Dijkstra's invariant, which was all vertices in the known set have the correct shortest path. And the way we maintain this invariant was always exploring nodes in the perimeter based off the closest distance. So I would argue to you that kind of the key worry you might have in Dijkstras is, suppose you have this known set, you've run Dijkstra so far, you have all of these nodes that are known, and say this node that doesn't have a label in it is distance 5 away from the start. And we're considering this vertex x that has an edge weight of 3 between it. And so we'd propose that the distance is 8. And we're probably kind of nervous about, well, if I were to add x to my known set, how do I know that there's no shorter path, maybe through this node A, that is ultimately shorter than the proposed path from this blank node to x? Now, the worry there of finding a path or having a shorter path that we have yet to explore is kind of solved by the fact that we always add these nodes in the perimeter to our known set based on distance. So we always add the closest node. So the only way for x to be added to our known set before A is if this edge weight from this blank node to x is less than the distance from the blank node to A. In this little example here, where this path from the blank node to A to x is actually shorter than the distance from the blank node to x, we would not explore x first because we always explore the node with the closest distance. So we would add A to our known set first and then update x. So this exploring the closest is the key idea that enables Dijkstra's invariant. Now, what I want us to talk about for the rest of this video is how do we actually implement Dijkstras, going in a little bit more detail than what we talked about in the pseudocode. And then I want us to talk about how do we actually analyze the runtime of Dijkstra's algorithm. So implementing Dijkstras, probably the key thing that's probably hard to conceptualize is how do I go about actually keeping track of what's the closest unknown vertex and grabbing that efficiently. So it would sure be pretty convenient if we had some data structure that could store all these vertices and somehow give each one of them some kind of priority, such that I can grab maybe the one with the highest priority, which would correspond to the node with the closest distance, in an efficient manner. And it would also be really nice if this data structure let me update the priority of these nodes so that, once I find a potential shorter path, I can update these nodes. This data structure should instead of saying data structure, I should say ADT, this description of a data structure, should hopefully sound kind of reminiscent of a minimum priority queue, where we can order all the vertices, their priority, based off their distance. And we can always grab that closest distant vertex from our perimeter. Now, we kind of also need this extra behavior of changing the priority, even if something's already in there, which is exactly why in Project 3, we make you implement a heap that has this change priority function, because changing priority is very, very useful for something like Dijkstra's algorithm. So this is actually why we cover Dijkstras and graphs at this point right after heaps in 373, is because heaps have this excellent application for exploring graphs in some order based off this priority. So we're going to use priority queues pretty heavily here in something like Dijkstras. Now, what I'm going to show you in the next slide is a very similar version of the pseudocode, except I'm going to highlight in green a bunch of changes I've made now that we know we're going to use this priority queue as the data structure to keep track of all of our nodes. So I start by making my perimeter as a priority queue and I add the first node. My while loop is while that parameter is not empty. To grab the closest node, we just call remove min. And then in my update step, there's really just a simple case of, is this node already there or is it not? If it's already there, then I want to call the change priority to update its priority. Otherwise, I want to just add this new node to my priority queue, and it will add however that works. Now, one thing that's a little bit confusing about this pseudocode that I've shown you here is, and it's a little hard to see, is I actually took away that known set. So the known set is no longer there. The reason for that is we're actually able to implicitly track what nodes are known with this dist2 and the priority queue. Remember with Dijkstra's invariant, once something was marked as known, we were saying there would never be a shorter path to that node. So since that was our invariant, in some sense the known set was just storing redundant information. Because once something has been marked as known, then we will never find a shorter distance to it, which means this if statement here would always fail for any node in our known set, which in some sense made our known set irrelevant. That we didn't actually need it to store this because we would use the fact that we never found a shorter distance to know something was known. So this is kind of a clever way of representing this so that we don't need that extra memory. Now, this pseudocode here is going to be a really good reference for you when it comes to implementing Dijkstras on Project 4. So like kind of take this in your notes now, kind of star this part, which says like when you're working on Project 4, have this slide up for reference, because this is going to be the thing that's very, very close to what you implement in Project 4. Don't worry, we leave some things for you to figure out. For example, you need to figure out how are you actually going to represent some data structure like dist2 such that all of the nodes are mapped to infinity, because it's not clear how you're going to represent infinite distance away. That's something you have to decide in your implementation. We also, in the spec for Project 4, will describe some optimizations we want you to make in terms of memory usage or speed. So we want to make sure that your implementation isn't too wasteful in terms of memory usage. All of this stuff will be explained in the Project 4 spec, but this will be a really good starting point for you from where to start off from. Now, what I want us to talk about in the rest of the video is how to actually go about analyzing the runtime for Dijkstra's algorithm. So the first thing I want to mention before we kind of go into how to analyze these runtimes is to quickly remind us about some notation. So whenever we talk about a graph, remember we always talked about this in terms of a set of vertices and a set of edges. And I'm trying to draw out letters with my mouse, so please forgive the sloppy handwriting. It's not the prettiest way of writing. When we have this graph in terms of the set of vertices, the set of nodes, and the set of edges, which is a bunch of pairs of nodes describing a connection between them, whenever we're going to have an algorithm that operates on one of these graphs, we usually will define its runtime in terms of the number of vertices and the number of edges. We use this bar notation, which is notation from set theory to describe the size of a set. It's technically called the cardinality, but we'll just use the word size. So bar v bar describes the number of vertices, while bar e bar describes the number of edges. In all of my reading of describing what's going on in the slides, I'll just say v and e, and we leave it up to context to figure out, am I talking about the set of vertices or am I talking about the size? But that should be pretty clear from context. As a reminder, we sometimes use the letters n to describe the number of vertices and m to describe the number of edges. In this analysis, I won't use those, but do remember you'll sometimes see that. Okay, so now let's go about actually analyzing the runtime of Dijkstra's algorithm. So we start with making our empty maps, which should be constant time, and then initializing that distance 2 for all nodes to be mapped to infinity. That's going to take theta of v time. The reason being we have to go through each vertex and set its distance to infinity, except that start node. That's going to have to do an iteration per vertex. Now making this priority queue and adding one node to it should all be constant time. And now the more complicated stuff is actually analyzing this while loop. So there's a couple key things I have to argue to you about how to analyze this. The first is, how do you go about analyzing the number of times this while loop will run? So the first thing I would argue is this while loop will run at most v times. Now, why is that? Well, this perimeter is going to have it's going to have a node in it per node in the graph. We'll never add a node twice because we always make sure to change priority if it's already in there. And once we've kind of known the distance of a node, once we've added it to this known set implicitly, well, we'll never add it back again. And so this perimeter at most will have v things in it. And so this while loop will kind of run through at most v times, so once per node in the graph. Now, additionally, if we think about this runtime of this remove min, I would argue that that's going to be a log v operation. Now, where does the log come from? Well, that comes from the fact that we're using a priority queue. Remember, almost all of the operations on priority queues that involve modifying the structure would take that logarithmic time. And then the question is, how many nodes or how many elements will be inside this priority queue? Well, in the worst case, there will be v elements in this priority queue. You can construct a graph where right after the start node, there are going to be all v elements. Consider a wheel where you have a start node in the middle and then a bunch of nodes coming out in a circle outside of it. In that case, you'll have something like v vertices right directly in your neighbors right away. And so your perimeter at most will have v things in it. So that's why this is log v. Worst case, there are v elements in the perimeter. And so now we need to go into actually analyzing this inner for loop. And what I would say here is that this is actually going to be really hard to do. The reason is this for loop runs a different number of times depending on which node you were at in this inner or this outer while loop, right? Each node has a different number of out neighbors. And so it's really hard to analyze the number of times this loop runs, this inner for loop. So just like with BFS, we're going to do this kind of strange technique where instead of trying to figure out the number of times this loop runs, we're going to make an argument about how many times this loop run in total over all iterations of the while loop, over every iteration of this while loop that will happen. How many times in total will this for loop run? And what I would argue to you is that this will run a total of theta of e times. Now, why is that? It's actually a very similar reason to the argument for BFS we saw last time. This loop runs over all the out edges of the given node u. Since this while loop is going to loop at most over each node u once, then this inner loop is going to loop over all of the outer edges of each node u. And if you loop over all of the outer edges of all of the nodes in the graph, that's just the total number of edges in the whole graph, right? There's no edge that's kind of floating around out there that's not connected to any nodes. Edges have to be connected to a start node and a destination node. And if we loop over all of the nodes and get all of their out edges, that should be the same as just all of the edges in the graph. So this is kind of pulling out this loop from our analysis. It's no longer trying to analyze it inside the while loop, but analyzing it over all of the runs of the while loop. So we're going to say that this is total of O of E time. Now, all of this work in here, I'd argue, is just constant time because it's just looking up things in map, doing an if statement, all constant work. And then the updating the priority queue, just like with removing min, in the worst case, there are V elements inside the priority queue. So both of these operations would be log V time. Now that we've analyzed all of these small parts, we can start putting them together. So this first part of this outer while loop would run in V log V time. Why? Well, because that while loop runs V times and that one operation takes log V times. So it'd be something like V log V. Now, what about the rest of that loop? Well, reminder, this total of E iterations is all about over all iterations of the while loop. We're not going to multiply all of this stuff by V because we've kind of already done this in this kind of total number of iterations logic. So this for loop is going to run in total theta of E times and do kind of in the worst case log V work. So in total, this kind of section of the code will run in E log V time. Then the total work of all of Dijkstras is just the addition of this, V plus log V plus E log V. And since V log V, this term up here, dominates V, we drop the V term. Now, you might be wondering, why can't we simplify this further? Well, we don't know which of V or E is larger. We don't know which of these terms will dominate. Now, one thing I want to remind you of is sometimes we think of, let me just change my pens. Sometimes I like to think of this Dijkstras runtime as comparing it to that BFS runtime. So remember for BFS, it's hard to draw dots. We had this theta of V plus E. Very atrocious handwriting. O of V plus E. This runtime for Dijkstras is very, very similar, except on each iteration of these loops, we were working with this priority queue. So we multiply each of these terms by this log V. But besides that, the runtime for Dijkstras is very, very similar to the runtime of BFS in terms of how do we go about analyzing it. So if you found this confusing, going back to BFS and understanding why the runtime is V plus E is very, very important. Now, one thing I should mention is that sometimes people, if you look up the runtime of Dijkstras on the internet, you'll see that people just list the E log V term. And that's because they're assuming that the number of edges is larger than the number of vertices. So if they're assuming that, then that's the appropriate answer. But I really like this answer instead, because it's very precise in terms of kind of being able to answer cases where the number of vertices is smaller than the number of edges, or if it's larger. So that's kind of all I want to talk about in terms of running through the runtime of Dijkstras. The most important thing is being able to understand the pseudocode, because it's going to be really, really helpful in terms of implementing your project for. And understanding the technique here of kind of pulling out this for loop over all iterations of the outer while loop is really, really helpful when it comes to analyzing graph algorithm runtimes.